So what we're going to do is we're going to take this region of 1 over x from x equals 1 to x equals 2 and take it around the line x equals 3. So effectively, we're going to end up with something over here that looks like this. We're going to have this is going to have revolved around here. And we can either, well, I guess, yeah, we haven't done shells yet, so we definitely won't do this using shells. Since we're revolving it around a line that's a vertical line, that's going to tell us that the slices that are perpendicular to that line or in the x direction, which makes the thickness of dy, will be these little rings, right? Or these washers. So we got to do this all in terms of y. And so then we need to look at what the outer and the inner radii are of this. And so the inner radius, actually, let's look at the outer radius first. The outer radius always goes from this line of x equals 3 to this line of x equals 1, right? The furthest left portion of our region is always indicated by the line x equals 1. So the outer radius is always the distance from 1 to 3, which would be 2. Okay. Right, so we're going to say our outer radius is always 2. Everybody good with that?
Yeah.
Okay. Now our inner radius is sometimes bounded by the line x equals 2, but it is also sometimes bounded by the function 1 over x itself. So if we go from a y value of 0 up to this y value of 1/2, what is the inner radius equal to? It's just this 1 unit. Everybody agree with that?
Yeah.
But when we go from 1/2 to 1, like I said, our outer radius stays the same, but our inner radius, not from y equals 0, from y equals 1/2 to y equals 1, our inner radius is different than that, right? So we have to break this down into the entire length here is 3, and this length is x. And you always have to remember to measure x from the y-axis going to the right to where our function hits. And so our radius is 3 minus x. And because we have y equals 1 over x, that would tell us that x equals 1 over y. So this would be 3 minus 1 over y for our inner radius. Everybody good with that? John, you were the one asking. Does that make sense?
Yeah, that makes sense.
And now we just simplify and evaluate. So this is pi times the integral from 0 to 1/2 of 3 dy. And this is pi times the integral from 1/2 to 1. Well, this becomes 4, and then 3 minus 1 over y squared is going to give us a 9 in there, right? So it's minus 4 minus 9 is going to be a -5. And then the 3 minus 1 over y, when I multiply the 3 by the -1 over y and the other -1 over y by the 3, it's going to give me a -6 over y. And with the negative there, that'll be plus 6 over y. And then -1 over y times -1 over y is 1 over y squared with the minus, so minus 1 over y squared dy to simplify what's inside of there. And this should now become pi times 3y from 0 to 1/2 plus pi times -5y plus 6 natural log absolute value y And then negative y to the negative 2 should become plus 1 over y from 1/2 to 1. And from there, you just evaluate 3/2 pi minus the 0, and then plus -5, 6 ln 1 is just 0, plus 1, and then minus, that's what, -5/2 plus 6 ln1/2 plus 2. And I don't know, comes out to be something. -5 plus 1 is -4, minus 2 is -6, and then plus 5/2. What is that? That's -7/2. So we got 3 pi over 2 minus 7 pi over 2. And then this is -6 ln1/2. Which gives us -2 pi, and then minus 6 pi. And I prefer to write this as ln1 minus ln2, and the ln1 goes away, so that becomes -2 pi plus 6 pi ln2 units cubed. Good or no? Good. Cool. Anybody else have any questions on that one or any of the other ones? Everyone's good? All right. So we will move on to doing what we call volume using cylindrical shells. So what this means is, instead of slicing this thing vertically or horizontally and getting a circle or a washer and a circle with the circle cut out of it, when we revolve it around, we're going to take what we call a typical rectangle from the region and revolve that typical rectangle around, making a hollow cylindrical shell. Think things that look like, an empty paper towel roll or an empty toilet paper roll. And just a very thin, hollow cylinder. So let's suppose we were just thinking about, and we'll go through all this stuff in a second. Suppose we were thinking about just some function from here to here. So here's our function, and we're going to revolve it around the x-axis. And it doesn't matter what this function is. We want to revolve it around the x-axis. So what we'll do is we will draw one little rectangle in there. Try and make it actually look like a rectangle that has a very small thickness in the y direction here. This would be dy. And we'll draw that rectangle so that it is parallel to the axis we're revolving it around. And we're just going to revolve each little rectangle around it, making a hollow cylinder. And we're going to do that with an infinite number of little tiny rectangles throughout it. And they will all sit inside of each other. So the ones that have a smaller radius will be inside the ones that have a larger radius. And these will all fit together to make up the entire volume of it, because the ones down here will have almost no radius to them and almost no gap. And by the time you get down to the y-axis, the x-axis, you'll just be, effectively revolving the x-axis around itself, which is filling in that last little gap of the interior of each of these other ones. And so they become very short, they have a very small height, the closer the function that we're using gets to the line that it ends at. So some of these will be very, 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 very short little cylinders with very little height to them, but they will be very wide. And then the next one will extend just a little bit outside of it. In terms of like height, it'll have a little bit more of a height extending to the left of the other one, but it will fit inside of it, and so on. They'll all fit inside of it. And the best analogy I can come up with for these is kind of like the idea of what a Russian nesting doll is, where you've got like the wooden little figure and you open it up, and inside of that is another one that looks exactly the same.
Yeah.
And then you open that one up and look inside of it, there's another one that looks exactly the same. Well, that's effectively what we're doing here, is except that they don't completely fit inside. Sometimes, because the heights are getting larger as the function gets wider here, they're sticking out of it, but they still fit inside of each other similarly to that. Does that conceptually make some sense, hopefully?
Yeah.
Yeah.
So there's just like a bunch of shells, pretty much, and we
Yep.
have to calculate the volume of those shells. Is that what you're saying?
Yeah, they're shells of a cylinder, basically. They're just like hollow cylinders. So, imagine you had, like I said, an empty toilet paper roll, and then you had another one that was just a little bit, had a slightly smaller radius to it, but was a little bit longer. You could fit it inside of it. It would stick out a little bit at the end, right? But it would, would still fit inside of it. Right?
Okay.
Radius would be a little bit smaller. And then you had another one that had a little bit bigger of a radius, but was a little bit shorter, and it would fit outside that first one that you had. And you just pile those all together infinitely until you filled up all of the space of this solid.
Okay, cool.
Does that conceptually make sense to everyone?
Yeah, conceptually.
Okay. So, question is, how do we find the total volume? Well, we have to find the volume of each one of these little cylinders. So in order to do that, we need to find the lateral surface area of one of them, right, which is just the surface area going around, and then multiply that by how thick it is. And so its thickness is in the y direction, dy, and the surface area should be 2 pi times the radius times the height, or the altitude. Right? And so this is the lateral surface area. And then we multiply it by the thickness to get the volume of each of these little shells. And so we're summing together 2 pi r h, 2 pi times the radius times the height, times the thickness, infinitely using an integral to find the full volume of this shape, right? 2 pi r is the circumference times the height, should be that lateral surface area, and then the thickness of it would give it some volume. And so the convenient thing about this is, for example, this one right here could be done if I revolve this thing around the x-axis, right? I could slice it and get a disk, couldn't I? I could do this one in terms of like a typical solid of revolution with these circular cross sections. True? Ignoring the shells for a second,
Yeah.
couldn't we do this the way we'd always done it? And if I'd done it the way we always did it, it would be done in terms of what variable?
X.
X. But if we do it this way, we'd be doing it in terms of y. And so depending on what this function is, and maybe it's not a function, maybe it's just some relation between x and y that does some weird stuff like this, right, that we're trying to revolve around the x-axis. It's going to allow us to use the other variable, just in case the equation that we have won't allow us to do it in terms of x. So sometimes there'll be problems, and not for this class, but in math in general, there will be problems that you cannot use the disk or washer method with. You have to use these shells just because of the nature of the equation that's given to you and the axis that you're revolving around. So this gives you the tool that no matter which direction you're revolving the thing around, if you're revolving it around something that's horizontal, you can now do it in terms of x or y. And if we were trying to take this thing, let's say, and revolve it around the y-axis, we would just draw these shells this way. And I could do it in terms of x going around a vertical axis, whereas normally we'd have to do it with a cross-sectional slice this way, right? And we'd get these little things that have holes in them, and we get the washers if we did it in terms of x, or we could do it this way with shells and do it in terms of y. So whether we're revolving around something horizontal or vertical, we should be able to do it all in terms of x or y, depending on which method we want to choose. Does that make sense to everybody? Why this is sort of an important thing to be able to do? Even though the College Board doesn't think it's that important, so they don't require it.
Did they used to require it?
No. To my knowledge, it has never been a requirement for the AP test, but I mean, it's in any other Calc 1 class, at community college or college level. Of course, they're going to teach you this method. I mean, I have no clue why the College Board doesn't include this. It's also not included in the BC curriculum, which makes no sense to me either. So it's beyond me why they don't think that it should be on there, but it should be. So this is what we're going to do. We're going to figure out whether its thickness is dx or dy. So if we're doing shells and we're revolving around something that is horizontal, it will always be dy. And if we're revolving around something that's vertical, it will always be, I wrote dy down here, didn't I? Wow, I wrote these backwards. This is dy and this is dx. If we're revolving around something that's vertical, it will be dx. We'll find the radius. So, there's our radius, or here's our radius. We'll find our height. There's our height, and there's our height. And we'll just multiply 2 pi times those and sum them all together with an integral. So let's take a look at this one. I stole this picture from a textbook. It's already got the height and the radius sort of written out for you. But we're going to take a look at y equals the square root of x between the x-axis and x equals 4, revolving it around the x-axis to make a solid. And so just because my artistic ability is garbage, I wanted to put in one where you can sort of see, and they've sort of got this done even more three-dimensionally than I would ever be capable of doing. But hopefully that gives you a general idea of what the shells look like. And you can imagine another one that's, a little bit wider just outside of this one, but a little bit shorter. And another one right in here that's a little bit narrower that fits inside of it, but that sticks out, extends a little bit beyond it. So hopefully that visual helps those of you that might have been having trouble visualizing it with my garbage pictures. Okay. So here's our rectangle. We drew the rectangle. Right, with an infinitesimal thinness to it here, and we revolved it around the x-axis. What is the thickness of this shell? In which direction is it infinitely thin?
Dx? No, dy.
Dx would be extending this way. It's not infinitely thin this way. It is infinitely thin in this direction. Infinitely thin in the y direction. Anytime you're revolving around the x-axis or anything horizontal, your thickness for shells will be dy, which means we need to do everything in terms of y. So then we look at our radius, and this is really convenient. The radius, for any time you're doing shells around the x-axis, your radius will always be y. Always. Right? Because if I'm going around the x-axis, my function's sitting up here. Well, that radius is the distance from what I'm revolving around to that function. It's just y. And likewise, if we're revolving around something that's vertical, that radius, if you're going around the y-axis, will always just be x. But we'll look at and talk about that in a minute. So our radius is y, and our height, the altitude of one of our shells, and it's already given to us here, But we should see that this whole distance is 4, and this distance is x. And so our height ought to be 4 minus x, right? The distance from where a function hits to this vertical line. Remembering that x is always measured from the y-axis to the right. And there's our 4 full units. And so since y was equal to root x, x is equal to y squared. And so our height ought to be 4 minus y squared. Everybody good with all of that setup there?
Yes.
All right. So we should be able to integrate 2 pi times the integral from our lowest y value, because we're doing this all in terms of y. What's our lowest y value of our region?
Lowest y
Negative
value.
2.
Wait, what?
What is the lowest y value of our region? Region we're talking about is root x, x-axis, x equals 4.
Okay.
So what's the lowest value of this region between root x, x equals 4, and the x-axis?
0.
0. What's the highest y value?
It's just 2.
Yep, it's 2. Okay. And so now it's 2 pi times our radius times our height times our thickness, which should give us 2 pi times the integral from 0 to 2 of 4y minus y cubed. If we distribute that y through, which ought to give us 2 pi times 2y squared minus y to the 4th over 4 from 0 to 2. Good or no?
Was the 2 pi just from the original equation, and so we just removed the constant? Is that where that came from?
Yeah, remember 2 pi r, that's the circumference, times h gives us the lateral surface area. Right, that's the 2 pi rh, and then the thickness dy makes it a 3-dimensional thing with some volume to it.
Okay, thanks.
So this gives us 2 pi, and we'll plug in our 2. 2 times 4 is 8, minus 2 to the 4th is 16, minus 4, or divide by 4 is 4. I guess I should write minus 0 since it's all 0 if I plug in 0. And 2 pi times 4 gives us 8 pi units cubed. Good or no?
So on this one, where like the height was just conveniently like given,
Mhm.
will we usually have to find it? Or
Oh
will it
yeah, normally you'll
just-
have to find it.
Okay.
The only reason I just wanted this picture to be there, which is why the height was already given to us. I just wanted a nice picture that wasn't my garbage drawing. So
Okay.
yeah, normally you'll have to find the height. And all the rest of them will have to find the height, the ones that we'll do the rest of the day today. And so could this one have been done using a disk, right? Using a circular cross section?
Yes.
It definitely could have been. And in fact, in this case, it would have been a lot easier if we'd done it using a disk. How would we have done that?
It would have been dx, and you would have done it in terms of x.
Right, it would have been dx and done in terms of x. This was root x. This was over to x equals 4. So it should have been an integral of pi times the radius squared. And what would the radius be?
Y.
Yeah, it would just be y, which is root x. So it would have just been x. We'll write it as root x squared dx from 0 to 4. This would have been way easier, right? Pi times the integral from 0 to 4 of x dx. But we'll see that what would we have gotten? We would have gotten pi times 8 minus 0. We still would have gotten 8 pi. So get the same value whichever way we decided to do it. Right, if we decided to use disks instead of shells. Much easier that way. But like I said, not all problems are easier using the disk and washer method. Sometimes it's easier with shells, and sometimes you'll have to use shells to do it. So let's take a look at this one. Let's see if we can take the region bounded by 4 minus x squared, y equals 3x, and x equals 0. And we're going to revolve it around the y-axis to form a solid. So let's graph this first. What we had? We had 4 minus x squared. We had 3x. And we had the x-axis, right? And we're going to say, I should have said something like the region in the first quadrant.
I thought it was x equals 0, not y equals 0.
No, it was x equal. I thought it said the y-axis. Oh, no. Okay, yeah, you're right. My fault. X equals 0. Okay, there we go. X equals 0. Oh, that's much better now. So we're going to still say in the first quadrant here, though. We're going to take this region in the first quadrant here, and in fact, all.
And what axis is it revolved around?
That said the y-axis.
Okay.
So I'm going to just throw that graph that we just nicely got here into our chart. And we're going to say, I'll make this caveat, which I should have done, the region in the first quadrant. All right, so we're bounded by x equals 0, 4 minus x squared, and y equals 3x. Remember this region right here. And we're going to revolve it around the y-axis. So when we sketch our typical rectangle, we want to sketch it parallel to the axis we're revolving around. And we're going to get a cylinder that looks about like that. Everybody good there?
Wait, so why'd you pick that position for like the bottom to be there? Is that just like a random?
Yeah, I can draw it anywhere I wanted. I could have drawn my rectangle over here.
Okay.
Right, it doesn't matter. Right. They're all generically drawn, right? So I just try to draw it sort of in the middle of the region. I could draw any, any rectangle, revolve it around, and get any generic cylinder within here. So I generally try to draw one that's sort of in the center of the region.
Okay.
Okay. So what is the thickness of this? In which direction is it infinitely thin? Basically, is what I'm asking.
Yeah.
Dx. Okay. What is the radius?
X.
Should just be x, right? It's just the distance from the y-axis to that rectangle. That's my radius. My radius is x. And what's my height? My height goes from here to here, doesn't it?
Yeah, so would it be like 4 minus your function or something like that?
It would be my upper function minus my lower function. Right? Because no matter where I draw that rectangle within here, the upper bound of that rectangle is from 4 minus x squared. It's the height of the parabola. And the lower bound of it is the height of this function. So 4 minus x squared minus 3x. Everybody good with that height or no?
So wait, so what is so you took your upper function and then subtracted it from your lower function. What does that give you? Did that give you the space? No, not the 4 minus with the, just the upper minus the lower. Would that give you like the space below it? And then you subtracted that from 4. And that gave you the height. I'm just trying to, wait. Can you just explain it one more time?
Yeah, so, I mean, any rectangle that I draw in here is going to extend from the parabola to the line. True?
Yeah,
I mean, that's my region, right? The upper bound of my region is the parabola and the lower bound is this linear piece. And so no matter where I draw it from, that upper height is the y value of that parabola. Well, that's 4 minus x squared. And the lower point is the y value of that linear piece, which is 3x. And so the distance between a y value of 4 minus x squared and a y value of 3x is this y value minus this y value, or 4 minus x squared minus 3x. But if I said this was 9 units up and this was 3 units up, well, you'd say to me that the height of it is 6, right? You do 9 minus 3. Well, this is 4 minus x squared units up, and this is 3x units up. So it's 4 minus x squared minus 3x.
Okay, thanks.
Everybody good there now on the height?
Yeah.
Okay. And so if this was the AP test and you didn't have Desmos sitting there to tell you that this intersection point was 1, 3, you'd want to set 4 minus x squared equal to 3x and solve that quadratic. X squared plus 3x minus 4 equals 0, giving you x minus 1x plus 4, and telling you that the intersection point there was x equals 1. And there was also one at -4 that we don't care about because that's not in our region. And you would go in and integrate 2 pi integral 0 to 1, leftmost x value to rightmost x value, radius times height, dx. Everybody good with that so far? And what do we end up with? Three pi over 2 units cubed. Good or no?
So for the AP test, would you have to conceptualize like all of these drawings?
Yeah, I mean, you'll need to know how to graph those functions and put it on. Depending on the problem, sometimes they give you a graph and sometimes they don't give you a graph. So generally, if it's a more complicated function, they'll give you the graph. But if it was something like this, I wouldn't count on having the graph given to you. You'd have to sketch this yourself and find the region. Most likely.
Thank you.
Yep. And could we have done this in terms of y using a disk?
Yes.
Yes.
We could have, but it would have been a heck of a lot more difficult because first off, we'd have to do it in terms of y, which would mean we'd have to turn y equals 3x into x equals 1/3 y. And we would have to turn y equals 4 minus x squared into x equals the square root of 4 minus y, which would have been a pain to start with. And then for some of our y values, from 0 to 3, the linear piece is to the right of this line. So we would have had to do 0 to 3 of the linear, and then we would have had to do 3 to 4 of the root function that we got by solving this. We would have had multiple integrals to complete and lots more algebra to deal with. So in this case, this way is probably actually quite a bit quicker and easier. Well, we could have done it in terms of y if we wanted to. All right, let's look at another one. And this time I won't go into Desmos, we'll just sketch it ourselves. So we've got 2x minus 1. That's not very good. That looks better. 2x minus 1 and root x. And x equals 0. So this region right here is what we're looking at. And we want to revolve it around the line y equals -2. Everybody good with that setup?
Yeah.
Okay. We'll draw a typical rectangle. That was way bigger than it should have been. That we're revolving around y equals -2. And we're going to need to figure out a couple of different things here. One, what is the lowest y value in our region? That should be -1. And what is this value up here? What is this point of intersection here?
1, 1.
1, 1, right? Should be able to just kind of see that. If I plug in 1 to both those, we get 1. And so since we're going around the line y equals -2, we're doing this with a thickness of dy. And we need to figure out the radius, and we need to figure out the height. Okay. So first off, our radius, what is our radius going to be?
Would be 2 minus y or something like that.
Not quite 2 minus y, but our radius should be 2 plus
2 plus y.
Radius should be 2 plus y. And then what about our height?
Is it just x? Right, because isn't the direction you go in the x direction?
Oh yeah, we are going in the x direction, but that height is sometimes bounded on the left by the x-axis or by the y-axis, and sometimes by the root function. True?
Would it be the root function minus x equals 0?
No, because the height is in this x direction. And so it's got to be from -1 to 0, right, where the y-axis bounds the left and the linear piece bounds the right. It's got to be the linear piece minus 0. But then from 0 to 1, it's got to be the linear piece minus the square root function. But they need to both be in terms of y. So from -1 to 0, our height should be, well, y equals 2x minus 1 gives me x equals y plus 1 over 2. So our height should be 1/2 y plus 1/2. But from 0 to 1, it should be this 1/2 y plus 1/2, this x value, minus this x value, and that would be y squared. Good or no?
Wait, so why are we separating it from -1 to 0 and 0 to 1? I don't get that.
Because the height of these cylinders from -1 to 0 stretch from the y-axis to the linear function, but from y equals 0 to y equals 1, they stretch from the square root function to the linear function. A different function bounds the left side of my region, depending on where I'm at. So what do we have? We had 2x minus 1, right? And we had square root x. So for the piece from -1 to 0, I guess I'll put in x equals 0. For the piece from -1, from y equals -1 to y equals 0, the height of these cylinders stretches from the linear to the vertical line. But from 0 to 1, it stretches from the linear to the square root function. So it has to be split up into two different integrals because we have different things that bound the left-hand portion of the region. And that left-hand portion of the region is part of how we find the height of each of these cylinders. Does that make sense?
Yeah.
Yeah.
Yeah, I mean, anytime we're measuring something in this direction, this horizontal direction, we have to look at what bounds the left and what bounds the right. And what bounds the left changes depending on the y value. What bounds the right portion of the region doesn't, but what bounds the left portion of the region does. And so we have to split it up. So this should be 2 pi times an integral from -1 to 0 of 2 plus y times 1/2 y plus 1/2 dy plus 2 pi times an integral from 0 to 1 of 2 plus y times 1/2 y plus 1/2 minus y squared dy. And those could easily enough be distributed out, and then you could integrate them and get your answer, but I'm not going to bother doing the distributing. That's just a bunch of arithmetic. The setup is the part I'm most concerned with you being able to get. Everybody good or no?
Can you explain how you got the height again from 0 to 1?
Yeah, from 0 to 1, I'm looking at the distance from the linear piece to the square root function. Right, it's the, if I were to, let me try to make that a little, it's just this piece. And so this
I see.
is what we're looking for. This little piece here is x1, we'll say, and this larger piece here is x2. x2 comes from the x value of the linear, and x1 comes from the x value of the root function.
Okay, thank you.
Mm-hmm.
Can you explain how you got the radius?
Yeah, the radius is the distance from y equals -2 to however high up here I go on my function. And so that will be 2 to get from -2 to my x-axis, plus whatever y value I've gone up above the x-axis. So, if this was 1/2, it'd be 2 plus 1/2. Right? And even if I was down here at -1/2, it'd be 2 plus -1/2. So I'd have a radius of like 1.5. So it's the distance between the line you're oscillating around to the x-axis, and then plus y.
Got it. Thank you.
Okay. How would this change if I was revolving around the line y equals 5? would the thickness change?
No.
No.
What about the height of each of these cylinders? They'd be going in a different direction, right? But that would only affect the radius. Wouldn't the heights of them still be exactly the same?
Yeah.
How would the radius change? The radius is now this, right?
Yeah.
So what would the radius become?
5
I
minus
minus
y.
5.
5 minus y, right? The total distance of 5 from the x-axis to the line we're oscillating around minus however much we've gone up, which is y. So this is the only thing that would change. And if you take an integral going around one line and switch it to another line using shells, the only thing that will ever change is the radius. So we would just rewrite this whole thing with 5 minus y's instead of 2 plus y's, and the rest of it would remain identical. Good or no?
Could you have done this one without cylindrical shells?
No,
It
of
would have
course,
been
yeah.
a lot harder to do without.
Actually, it would have been a lot easier, but
Okay.
yeah, I mean, we could have revolved this region around y equals -2. We would have gotten washers, right? An outer radius, we'd be doing it in terms of x, and we have an outer radius of this y value and an inner radius of this y value. It would have just been the outer radius squared minus the inner radius squared. So it would have just been root x squared minus the quantity 2x minus 1 squared. So this one, you wouldn't want to do it in terms of shells if you didn't have to. I haven't said use shells.
Is there a way for us to tell whether we should use the shells or not?
I mean, basically, if you're revolving around something that's horizontal, right, you know that doing it using disks or washers will be done in terms of x. So look and see if there's always one function that's above the other function. If that's the case, then it's probably a good method. If you're doing it around the horizontal axis and you are looking at doing shells, look and see if there's one function that's always to the right of the other function, or one function that's always to the left of the other function. And if that is the case, it's probably a good idea to use shells. So in this case, since the left portion of my region was different depending on what y value I was at, shells is not a good choice, even though that's what we did, because that's what I said we had to do. But because one function is always above the other function, doing it in terms of x is a good choice. So I would use disks or washers for this one. So just kind of look at what the region you're looking at is, and if one function is always to the right of another function, doing it in terms of y is going to make life easy. If one function is always above the other function, doing it in terms of x should make it pretty easy, generally. Does that help?
Yep.
Okay. All right, last problems we're going to do. So we are going to use shells to find the volume we get if we take the region enclosed by the y-axis and this function, which is just this region right here, and revolve it around all these different lines. The x-axis, y equals 1 and y equals 8/5. So let's start with the x-axis. Actually, let's start with talking about why we have to use shells for this. So if I were to revolve this region down here, couldn't I slice it and get some washers? Doing it in terms of dx, couldn't I slice it that way and get some washers?
Yeah.
Yeah, we definitely could. And the problem with that, though, is the outer radius is the y value of my function, And the inner radius is also the y value of my function, right? So how am I going to do that? I'd have to put this thing in terms of y equals something in terms of x. And then I have the same function giving me the outer and the inner radius, which is going to be a pretty big problem. Would you guys agree with that? Hopefully
Wait,
so.
so the issue's that the inner radius is the same as the outer radius? Is that what you said?
Well, I mean, it comes from the same function. So the same function bounds the upper part of the region and the lower part of the region. That's part of the problem. The rest of the problem is that taking this and solving for in terms of x, right? Solving this for, y equals something in terms of x is not the easiest thing for you to do. In fact, I doubt that any of you know off the top of your head the formula to solve a cubic, since it's a fairly lengthy little formula. And so that's not going to work out very well, right? You won't be able to solve this, put this all as y equals something in terms of x. And even if you could, the upper and the lower bounds of your region are the same equation. So that's an issue. So the good news is we could use shells. And if I were to try to use shells, first thing I would do is I would draw a typical rectangle and just sketch this shell that goes around it. And we would think about what's the thickness of this going to be.
dy.
Yeah. The
Yeah,
y.
dy, exactly. Parallel to the x-axis, which means that it has an infinite thinness in the y direction. What's the height?
Just x.
Just the x value, right? This is just height as x. Well, what's x? X is 12 times y squared minus y cubed. And what's the radius?
Y.
Just y. Like I said before, anytime you're doing shells and revolving around the x-axis, your radius will always just be y. So as we set this up, we should have, and we should probably figure out what this point is, but what is this point here? What is the other value? If x is 0, y is 0. But also if y is 1, right? 1 squared is 1 minus 1 cubed is also 1. 1 minus 1 is 0. So that'd give us another x value of 0 when y is 1. So we should have 2 pi times, let's pull this 12 out. So 24 pi times the integral from 0 to 1 of y times y squared minus y cubed dy. And that would give us 24 pi integral from 0 to 1 of y cubed minus y to the fourth, or 24 pi times y to the fourth over 4 minus y to the fifth over 5 from 0 to 1. And what does that give us? 24 pi times a fourth minus a fifth. And what's a fourth minus a fifth? That ought to be 5/20ths minus 4/20ths, which ought to be 1/20th. Divide those both by 4, and you get 6 pi over 5 units cubed. Good or no?
Good.
All right. What about if we were going around the line y equals 1? Would the thickness change?
No.
Would the height change?
No.
Would the radius change?
Yes.
Yes.
Yep, I'm going around y equals 1. The radius now becomes
1 minus y.
1 minus y. Okay. 1 minus y. So all we would do is the same thing. We'd have 24 pi, because I'm going to pull that 12 out again, times an integral from 0 to 1 of 1 minus y times y squared minus y cubed dy, which would be what? 24 pi times the integral from 0 to 1. Let's see here, if I distribute all this out, 1 times y squared is y squared. 1 times negative y cubed is negative y cubed, and there's another negative y cubed, so negative 2y cubed, and then plus y to the fourth dy, giving us 24 pi times y cubed over 3 minus 1/2 y to the fourth plus y to the fifth over 5 from 0 to 1. And what does that give us? 24 pi times a third minus a half plus a fifth. I don't know, what's a third minus a half plus a fifth? Third minus a half, that would be 2/6 minus 3/6, that's negative 1/6. So we get negative a sixth plus a fifth, or a fifth minus a sixth. And a fifth minus a sixth ought to be 6/30 minus 5/30. Try to be 1/30. So 24 pi over 30. And once again, divide those both by, this time by 6. Everybody good there?
Yep.
What if I wanted to go around the line y equals 8/5? What's the thickness? Still dy, right? What's the height? Still 12 times y squared minus y cubed. What's the radius?
Just be 8/5 minus y.
8/5 minus y. 24 pi times the integral from 0 to 1 of, let's see, if this was an 8/5 minus y, I'll write it out, 8/5 minus y. Not y squared over anything, y squared minus y cubed. Distribute it all out. That'll be 8/5 y squared. That'll be minus 8/5 y cubed minus another y cubed. So that'll be minus 13/5 y cubed. That's unplugged. And then plus y to the fourth dy. 24 pi times, let's see, what does that become? That should be 8y cubed over 15. And this one should become minus 13y to the fourth over 20. And this one should become plus y to the fifth over 5 from 0 to 1. Everybody agree with that? Plug in your 1, plug in your 0. Common denominator there is going to be what? Looks like 60. So this will be 32 minus 26. No, 32 minus 39, right? Which will give us negative 7/60 plus 12, so that'll be 5/60. 5/60 ought to be 1/12. So So that gives us 24 pi over 12 or 2 pi units cubed. Shells. Important, not required for the AP test, but required for some problems. This one could not have been done using disks or washers in terms of X. And I think hopefully my point is well taken that the only thing that changes if you move the line you're revolving around is the radius. Height and the thickness stay the same. Any questions on cylindrical shells?
Are we gonna get a worksheet to practice?
Yeah, you will.
Okay, sweet.
Which will in fact be the last assignment that is new material for the year.